Hello and welcome everybody to the SummerSlam Special Edition. I'm Sally Allen, Executive Director of the Livermore Lab Foundation, and we're so glad that you could join us today. This event is special in that it showcases the top presenters from this summer's cohort of student interns at Lawrence Livermore National Laboratory. The research that you're going to hear about today represents the full scope of Livermore's programs, from computing and engineering and physical and life sciences to global security, weapons and complex integration, and the National Ignition Facility. Today's presenters were selected by their mentors and senior leaders for their exceptional work and presentations, and showcasing the depth and breadth of Livermore's world-class science and technology. Here is a quick glimpse of our agenda for today. As I mentioned, this is our third annual SummerSlam Special Edition, although Livermore Lab Foundation has partnered with the lab since 2018 to recognize poster session participants and top presenters. We'll have 14 presentations today from 15 students, and we've allotted approximately 5 minutes for each talk, including a little bit of Q&A at the end of each talk, and hopefully with some time at the end of the program for additional questions. More about that in a minute. I just would like to take a moment to share a little bit more about the foundation. Hopefully many of you are aware that there is a Livermore Lab Foundation, but you may not know as much about what we've been up to since our inception in 2016. We're an independent nonprofit organization and philanthropic partner to Livermore Lab, and we're dedicated to advancing science and inspiring future STEM leaders. Our focus is really to harness the power and promise of the lab's expertise for the greater good. And as a 501c3 nonprofit, we can enable opportunities for the lab to explore creative partnerships with philanthropy, academia, industry, and the community to address some of society's greatest challenges. As you know, Livermore's multidisciplinary approach and commitment to team science makes it uniquely positioned to address critical issues in energy, healthcare, climate resilience, biosecurity, and much, much more. The foundation has invested funding over the past several years in 2 key areas to support some groundbreaking research. First, in healthcare, we have provided early stage funding for several research projects that are leveraging the lab's expertise in computing, engineering, and the biosciences to better understand, diagnose, and treat rare diseases in neurodegenerative disease and, for example, ALS in some of our early projects. On the other side of the spectrum in research, we have been working closely with the lab's Carbon Initiative team and others to help advance public understanding of the science behind technologies like carbon capture and carbon removal, and to help inform the policy and community decisions that need to be made to help California and others achieve carbon neutrality goals. Advancing science for the greater good also requires that we continue to bring new people and new perspectives to the lab and to STEM in general. And the foundation seeks to do this through various student STEM programs and opportunities each year. Here is just a quick snapshot of our 2022 programs, all made possible through our generous donor community and designed to provide meaningful connections through mentorships that hopefully inspire students like those you'll see today to pursue future educational and professional opportunities in the STEM fields. Every STEM program that we support would not be possible without the incredible leadership and contributions from our champions and allies at the lab. And I want to take a minute to just acknowledge and thank Dr. Joanna Albala, who is with us today on the webinar, for all that she's done to support science and education, both at the lab and in the community. So thank you, Joanna. Which brings me back to today's program. Here are just a few quick ground rules to get us started. All of you on the webinar should remain muted during the presentations, and we'll be spotlighting each of the students during their talk. Some of them are actually reporting directly from their lab campus locations. And so unfortunately, they may not be able to turn on their cameras, which is why you may just see their name or their photo instead of their live image. So just wanted to put that out there at the beginning to understand what you'll be seeing. We'll also encourage you to use the Q&A function in the Zoom webinar features to submit any comments or questions as the students are speaking. And we will try to address at least one question, maybe two, if there's time after each talk. And then again, hopefully have some time at the end of our program for additional questions. And finally, today's event is being recorded. And so we will be uploading this to the Foundation's YouTube channel shortly, and we'll get word out to everybody who registered for today's event. So you can check it out if you're not able to stay for the entire program. And so with that, that wraps up the ground rules. I am going to hand it over to our very first presenter, who is Jonathan. He's from UC Merced. And as you kick us off, Jonathan, maybe you can share just again, your year in school and maybe where you're zooming in from today, and then we'll have you get started. Thanks so much.
Sure. Hi, thank you for the introduction. Yeah, I am a graduate student from UC Merced. This is actually going to be my final year at my PhD, so I'm planning to graduate by December, actually. Now, let's see. And my project over there involves mathematical modeling and studying autoimmune disease. But we're going to hear about the project I did today. So hello, everybody. Thank you for taking the time out of your day to come and listen to our presentations. My name is Jonathan Anzules, and I am a PhD student from UC Merced. Under the mentorship of Jonathan Allen and Jose Manuel Marti Martinez, I pursued the project of predicting COVID-19 variants and their function. The idiom of finding a needle in a haystack does a good job at describing what variant detection is like. Now, imagine that the haystack and the needle are constantly changing. The hay is now wood chips, toothpicks, or even pine needles. The needle is a safety pin, a metal wire, or even a metal pin. So now, due to the fluctuations of viral evolution, this is more or less what it's like to identify viral variants. In this figure, we see a small example of what my haystack and needle looks like, and plus points to those of you that can identify the difference. Now, the reality is that viral genomes can vary between 30,000 to 300,000 nucleotides in length. The challenges of variant detection is as follows. First and foremost is identifying the variant, then predicting the function, and then doing all of this before the virus has a chance to disseminate far and wide. Normally, we need an abundance of data and experimentation to determine whether a variant will be problematic. Fortunately, new techniques in data acquisition and machine learning has the potential to solve these challenges. Facebook research has collected all of the protein data that they could get their hands on. So they trained a massive transformer-based machine learning model that can detect variants and predict their functionality. My job was to determine whether this evolutionary scale model or ESM has the potential to be useful. So I collected thousands of COVID-19 genomes and their variants, and from that data, I pulled out the spike protein sequence. The spike protein is one of the most important parts of the COVID-19 architecture because it allows COVID to infect us. These figures that you see here are the predicted interaction sites of the spike protein that has been determined and predicted by the ESM. The X and Y axes are coordinates along the amino acid chain. The brighter the color, the more likely there is an interaction site. And the darker the color, the opposite. The figure on the left is the result of a non-mutated spike protein sequence. The figure on the right is the same sequence, but it has a 10% mutation in it. When we compare both figures, specifically the bottom right corners of both figures, we can see that on the figure on the right, there is, given this mutational set, this spike protein has lost functionality. Now, there's still a lot of work that needs to be done with this, but so far, this evolutionary scale model has the potential to be a very useful tool for variant detection. And that's it for me. Thank you for listening.
Thanks so much, Jonathan. Sorry, I was trying to turn my sound back on. Great presentation. What are your plans in terms of continuing this research or later this summer?
Well, unfortunately, and it really is a bummer. I was enjoying this work, but like this is the last week of my internship. But future steps would be to really, because to I see if I could make this model actually identify the variants, which I haven't gotten to, is a challenging part of the project. But I'm still going to be working with it because honestly, these are the skills of bioinformatics that are important right now, and where the field is really heading off to. So in my off time, maybe on the weekends during the day, me and my mentor have agreed that I should continue working on this if I could.
That's fantastic. What would you say was your favorite aspect of your internship at the lab this summer?
Being exposed to machine learning. I have been exposed before. I've worked on it before, but I've never worked on it on such a scale. And the new and cutting edge of machine learning is transformer models. And I really wanted to get my hands on that and try to just learn from it and interacting with that, getting all the sequences, organizing the data, interacting with the model and getting all of the results. It's really been an enriching experience for me.
That's terrific. Well, thank you so much. It's obvious you put a lot of work into that this summer, so we're happy you could be here today.
Yeah, thank you for having me.
Thanks, Jonathan. Okay, I'm going to move us along to our next speaker is Nathan Beck. He's from University of Texas at Dallas.
Yeah, so my name is Nathan Beck. I am from the University of Texas at Dallas. I'm a PhD student pursuing machine learning, in particular, the exact subject I'm presenting to you today, active learning. So I study under Dr. Rishabh Iyer, and for my mentors at the lab, I have Dr. Bhavya Kalkura and Dr. Brian Bartleson to sort of supervise this project. I find it easier to sort of say how much time I have left at my university than how long I've been here. So all being very well, everyone liking my thesis and not sort of stretching my time here out, I should be done in roughly a year and a half. So today I want to present the work that I did at the lab, which is an analysis of active learning methods in out of distribution drift settings. And before I get into the specifics of this, I'd like to sort of motivate, why it's even worthwhile to study this and what sort of impact it would have on the lab. So to start off with, I want to sort of introduce an encouraging use case. And in particular, the sort of area of interest would be to sort of accelerate the simulations that the lab does using these surrogate models that you hear about in machine learning. So the idea is that you can run a simulation to study some sort of physical aspect, but that simulation could take hours, perhaps even days to run. So the idea is you can take a deep neural network and basically replace the simulator with it. The idea is that you take the data that you're wanting to feed into the simulator and you label each of these data points with the expected output of that simulator. You train the neural network on that data, and then you can replace the simulator with that network. So the out of distribution drift comes into the play whenever you sort of start seeing data that's different than what you trained your model on. And this naturally occurs in these sort of simulations because the physics of the environment that you're simulating naturally shift over time. So to sort of remedy this, you need to select new training data to improve the performance, and you need to select, of all this new training data, you need to select new observations. And then you need to label them again with the output of that simulator before you start training. And typically you do this process iteratively. So you repeat the training and the deployment. The burning question is how do you even select that new data? Of all the instances that you could choose to feed to the simulator, label, and then retrain, which ones do you select? And that's where active learning comes into play. The fact of the matter is that labeling data is incredibly expensive. The sort of thing that I like to default to is the medical imaging field. I can't just walk into a doctor's office, go up to the physician and say, hey, can you label 10,000 images for me? Pretty please. They'll probably laugh at you or sort of expect you to pay them very large sums of money. And so active learning attempts to solve this labeling issue by choosing the best observations to label. In this case, the best ones to feed to the simulator, get their outputs, and then formulate that as training data for the network. So it reduces labeling effort, and suffice to say, many different active learning methods exist, and I could talk the full day about them. So I particularly won't do that for you all. And the crux of the issue now is the sort of out of distribution drift component. it's not really been heavily studied whether or not active learning methods will generate these, will encourage selection of instances that create models that can handle this sort of drift. So typically, you can do very well in selecting in distribution points, which sort of be like the physics that you have seen. But it's not heavily studied if these methods will select instances that produce models that will handle this new physics that you haven't seen. And so this work is we're evaluating all of these different methods using common metrics and data sets. And that's just about where I am now. We've seen mixed results where, yes, they do generate brittle models once they can't handle drift. And there are results that suggest that they do. So we're still working out the details there, but in summary, that's the work that I've been working on this summer. Thank you.
Thanks very much, Nathan. Great job. So I know we're a little short on time, but I did want to ask, again, similar question, what your next plans are, and if you plan to continue this research, and maybe how often you have to be retrained in some of this work.
All right, we're planning on extending this as a collaboration between my group, the University of Texas, and the lab. So suffice to say, we're going to continue running more experiments, and hopefully we'd like to actually devise a new active learning method that sort of solves this issue.
Oh, that's terrific. And what was your highlight of the summer, would you say?
Oh, I would, again, I like being, I was very much enjoyed being exposed to all the sort of different classes that were offered for the DSSI. Jonathan and I actually from the DSSI organization at the lab, and so getting to interact with other like-minded individuals and seeing sort of these techniques from experts at the lab was very enriching, and I very much enjoyed that part of my internship.
That's great to hear. Thanks so much, Nathan. We appreciated your talk. I'm going to move us on to our next speaker. We have Jalen Rose Clark from Norfolk State. Jalen Rose, you're up next. And don't forget to ask questions in the Q&A, folks. If we're happy to keep an eye on those and try to incorporate those as much as we can.
Hello, everyone. Good afternoon. My name is Jalen Rose Clark, and I'm an undergraduate student from Norfolk State University. So this summer, my research focused on fabricating and biofunctionalizing PVA and PEI nanofibers for rare earth element extraction. So the whole premise of this research, we wanted to find a more environmentally friendly process of extracting rare earth elements. And it's been found recently that rare earth elements are more abundant in coal mining byproducts than the coal itself. So we believe incorporating some type of solid liquid extraction process for these rare earths will allow us to mine for more elements while also making it the most effective process. So to do this, we want to incorporate electrospun nanofibers, which is this picture at the bottom you can see. So the first step is actually creating these nanofibers. So to do that, we electrospin them. So we are using two different polymer solutions, PVA, which is polyvinyl alcohol, and PEI, which is polyethylenamine. So we mix these two solutions and place them in our electrospinner. So the polymers are placed in a charged syringe. It's charged with positive voltage. And when the solution is pushed out of the syringe into an electric field, the solution properties change and it goes from being a liquid polymer to polymer fibers. So once these are spun, they're spun into a fibrous mat that essentially just looks like a piece of paper. So once we have our fibers, we want them to have an affinity for rare earths. So to do that, we immobilize something called a lanthanide binding tag. So these are just engineered short peptides that have an affinity for rare earth elements themselves. So once we attach those to our fibers, we need to test to see if our fibers will actually work as a filter. So we do neodymium adsorption and desorption runs, which is essentially just washing our filters with neodymium to try and see if it can extract neodymium out of water. And to measure the concentration extracted, we use UV-vis spectroscopy to measure the concentration of neodymium. And we introduce our neodymium solutions with an arsenic 3, and from that complex, we can find out how much was extracted. And so we've done multiple tests with different polymer solution chemistries, and we found that our fibers do extract neodymium from water. So from here, we need to improve our absorption capacity for our fibers. And this just looks like creating thicker fiber mats and ensuring that the solution chemistry of our nanofibers is optimal for immobilizing the peptide and for the chemistry that's involved. And we also want to incorporate fluorescence microscopy just to ensure that our samples have the right functional groups before we start testing, just so we're not just wasting steps. And that's my research.
Super. Thank you so much. So what led you to be interested in rare elements?
That's a great question. It was kind of just presented to me. I didn't really know much about rare earth elements themselves. I have a background in chemistry, so I'm kind of familiar with stuff like that, but it was definitely a new field, but it's been eye-opening and I definitely want to continue in it.
And are you about finished with your internship as well, or do you have more weeks ahead?
No, this is my last week, unfortunately.
One last question from the audience. Does this method scale to meet the problem at scale?
So we believe it can potentially scale up. We just need to produce or get more reproducible results. It seemed to be more effective than other methods that are being applied here, such as using like microbeads.
Mm-hmm.
So just comparing those two, ours seems to work better, but it's still a work in progress.
And do the filters clog at all?
No, not in that sense.
Mm-hmm.
They don't clog. Maybe after multiple washes, maybe after like hundreds of washes, they might not be reusable or usable anymore. So they might deteriorate over multiple washes. Got
it. And would you like to share sort of your favorite highlight from the summer or the best part of working at Livermore?
Being introduced to new things, just definitely been my favorite part. There's so many things out here, so many different projects people are working on. So it's been great to see everything.
Super. Well, thank you so much, Jalen Rose. It was great to hear your talk. Thanks so much. I think our next speaker I'm going to move us on to is Neera Jara, and I am going to be sharing her screen, her slides for her. So let me pull those up.
Hello, my name is Neera Jara Dengwatinawinit. I just finished my first year of undergrad at UCLA, and I will be presenting my project on extending and smoothing two-dimension equation of state simulation data. I'd like to give a quick thanks to my mentor, Jim Leake, and the other people here at the lab for giving me this opportunity. Next slide, please. So my project is part of a larger project called MUS, which stands for Multi-Phase Equation of State. MUS produces equation of state data tables, which are used in hydrocodes. Hydrocodes are hydrodynamic simulations that are used by various projects here at the lab. To produce accurate simulations, these equation of state data tables need two important things. They need to be accurate and they need to be smooth. Smooth because of the derivatives and second derivatives utilized in the calculations for these simulations. My project focuses on producing better electron thermal free energy data tables. In the past, MUS produced these data tables by combining the Purgatorial and Thomas Fermi model. Purgatorial is used because of its accuracy. As you can see in the bottom two left graphs, in the blue boxes, the data is very accurate and smooth, but outside of the blue boxes, the data becomes jagged, discontinuous, and just incomplete. To compensate for this lack of smoothness in Purgatorial, we also use Thomas Fermi. Thomas Fermi is not as accurate as Purgatorial, but it's very smooth. So this is the reason why we combine the two models. Next slide, please. So the way we've been combining Purgatorial and Thomas Fermi is by defining simple markers. For example, in the top three graphs, you see a line at 7 grams per cubic centimeter, where anything above that line, we use Purgatorial, and anything below that line, we use Thomas Fermi. You get the resulting right graph, which is continuous, smooth, and accurate. But that's a pretty simple data table. In the bottom three, you get a more complicated data table with two markers, one on the density axis and one on the temperature axis. But combining these two models still leaves some imperfections in the final data table, simply because these markers are just not flexible enough. This is where my project comes in. Next slide, please. So my project is on improving user flexibility and defining which area of the purgatorial table can be replaced by Thomas Fermi. As you can see, I've implemented a feature that allows the user to implement small little box regions in the purgatory table to be replaced by Thomas Fermi. And as a result, you can see the bottom right graph already looks a lot better than the graph from the previous slide. In the green box, you can also see that there are still some imperfections, and that's the result of both Thomas Fermi and purgatorial being jagged and incomplete in that region. Solutions to that would be interpolation or perhaps using a different model. Obviously, this project is still a work in progress, but with these implementations and improvements, hopefully this will benefit many groups here at the lab. And that's my research. Thank you.
Thank you. Sorry, I'm working multiple controls here, so I wanted to get back off on mute. Thank you so much. So maybe you can share a little bit about how you got interested in this, into this area of research in your project this summer, and sort of where you go from here.
Yeah, sure. So this was the project I was assigned to work on, so I didn't know a whole lot about it, but it sounded interesting to me, so I gladly read about it and learned about it. Right now, this project is a little bit on pause as I'm working on other parts of MEOS, but perhaps I will continue improving the electron thermal data table later.
Super. One of our questions from the audience, what would you name your new model, since it's a combination of the two previous ones?
So actually, the previous models of combining purgatorial and Thomas Fermi have been called Purga Extend with TF. We have TF, TF1, TF2, TF3, and I just finished making TF4. So not the super genius name, but.
I like your background. Were you able to get any tours of the computing facilities at the lab this summer?
No, not yet, but
Okay.
Hopefully I will.
Super. Great. Well, thank you so much, Nirajara, for your presentation.
Thank
I'm
you.
going to move us along. Our audience is a little shy today, so I'll remind folks you're welcome to provide questions in the Q&A. So our next speaker is Grant. Grant comes from UC Davis. We're going to hand it over to you.
I'm Grant Gogol. I'm just wrapping up my first year of being a grad student at UC Davis. This summer, at the lab, I worked on soil viral ecology, which is also where my graduate work focuses on too. So it's summer, and it's no secret that it's hot out. It's also no secret that dry seasons in Mediterranean climates, like here in California, are getting longer, while the wet seasons are getting shorter. What may still be a secret, though, is how the Earth's smallest biological entities may be responding to this changing environment and how these changes may be related to the carbon cycle in soils. I'm referring to viruses. These small little entities could potentially have a large role in nutrient availability and the carbon cycle in soils. We know that the soil organisms that viruses like to prey on, like microbes, which I mainly focus on, can play a role in the flow of carbon in soils, because these microbes like to eat all this tasty sugar and carbon present in soil and release that as CO2. Viruses can control this because they can infect their host and then make copies of themselves inside the host, causing the host to swell until they pop like a balloon. Viruses can also put their host in a zombie-like state, where they essentially take over the host and manipulate them, where they could potentially have their host eat more of this tasty carbon present in soils. It is unclear how this constant battle between viruses and their host and the environment changes when soils become wet and dry throughout the year, and the impact this may have on carbon in soils. My summer research focused upon these two questions. How do soil viruses respond to a changing environment, and how can these responses relate to climate change? Soils in Mediterranean environments go through periods where they are extremely dry and everything looks dead, but then there is a precipitation event that causes a huge flux of life and greenery, both above ground and below ground, as we've all seen around Livermore and other parts in California. Current methods looking at viral communities between these two extremes are looking at everything in the soil. This may include dead organisms or other organisms that may not be active and contributing much to their environment. Here in this study, we use stable isotope probing using a different flavor of water that is heavier and denser than regular water and does not negatively impact the organism's growth. Using this, we're able to focus on organisms that are active and growing in the environment, because they will incorporate this heavier, denser genetic material water into their genetic material. We could then take this genetic material and spin it really fast to separate this heavier, denser material, which we could then sequence to study these active viral populations and see how they change when the soils are dry compared to wet. Using this fancy water and genetic information, I've already been able to observe a difference in both active and non-active populations when comparing dry to wet soils. I will further link these changes in the populations to the flow of carbon in soils and how soil viral communities are responding to a changing in climate. And this research will be critical in understanding how the dry and wet seasons affect virus populations and their hosts, and how this affects the persistence of and flow of carbon in soils, which may be related to how viral communities are responding to a changing climate. And yeah, that's it. Thank you for your time.
Thanks very much, Grant. A really timely topic, especially here in sunny, dry California. What's your opinion of the state's, net neutrality goals? Do you believe we can reach carbon neutrality by 2045, as the governor is hoping?
I think it'll take a lot of work. I'm not completely familiar, but yeah.
Was it what got you interested in this subject matter?
Prior, I was studying microbial ecology, and then when I went back to grad school, I got exposed to the viral ecology, and it just took off from there.
Are there certain plants that are more susceptible to these viruses? I know at the lab, there's been a lot of study around prairie grass, for example.
I'm sorry, can you repeat that?
Well, I'm just curious if there are certain plants versus others that are more susceptible to these viruses that you're studying.
I'm not sure. I'm learning to focus on bacteriophages, so the ones that are affecting the bacteria in soils.
Okay. And did your studies primarily look at samples from in and around Livermore, or were you?
Hoplands, like grasslands, yeah.
Terrific. Well,
Yeah.
Thank you very much, Grant. It was great to hear your talk today.
Awesome, thank you.
Okay, I'm going to move us on to our next speaker, Jenny Gorman. Jenny's from Rensselaer Polytech. Jenny, take it away.
Hi, my name is Jenny Gorman, and I'm a mathematics PhD student at Rensselaer Polytechnic Institute. This summer, I worked with my mentor, Dick Berger, as well as Tom Chapman and my research advisor, Jeff Banks from RPI. And I'll be talking about the threshold of absolutely unstable stimulated Raman backscattering and the simulations we use to observe it. On the left, we see an illustration of a Hall-Ram in NIF, and laser-generated plasmas in Hall-Rams can result in stimulated Raman scattering of laser light. So these Hall-Rams consist of an outer cylinder with a hole in the top and the bottom and an inner fuel capsule, with the hopes of symmetrically imploding this fuel capsule. So laser light is directed into holes in the top and bottom and aimed at the inner walls of the Hall-Ram, forming a plasma. And within this plasma, electromagnetic waves can scatter off of an electron plasma wave, which forms something called stimulated Raman scattering. This scattered light can be undesirable because it can bounce back out of the holes in the Hall-Ram, at best wasting the drive energy, and at worst possibly damaging the laser optics. And within the Hall-Ram, it can spoil the symmetric implosion of the fuel capsule. Our goal is to understand experimental measurements of stimulated Raman scattering using simulations. So the essentials of SRS can be understood using two coupled equations, which are shown at the top left here, which represent a uniformly dense plasma with a finite length. In this plasma, we have some incident laser light traveling, say, to the right, an electron plasma wave traveling in the same direction, which is denoted by A2 in these equations. We also have backscattered light traveling in the opposite direction, denoted by A1. When the incident laser light and the backscattered light match up in a certain way, it can fuel growth in the electron plasma wave. And this growth in the electron plasma wave can fuel growth in the backscattered light wave as electromagnetic waves bounce off of it more. This can lead to a parametric instability that can grow exponentially. This growth can be convective, growing in space, or absolute, growing everywhere in time. Motivated by experiments that show we're dealing with higher temperature electrons, we decided to study absolute SRS, growing everywhere in time. This model is being used to benchmark a larger kinetic code called Loki with a lot more physics involved. So our preliminary simulations show that we have an exponential rate of growth when we're above some given threshold. So the plots along the top are the log of the scattered light and the electron plasma wave over time. And we see on the left, when we are at some threshold, after initial information has propagated across the solution, we see no more growth over time. Whereas on the right, after this initial information has propagated across the solution, we observe exponential growth. This was expected from our simulations. And so our next goal is to use these simulations to compare the exponential growth rates with exponential growth rates from the larger kinetic code, and then compare those as well as the envelopes of our waves, which are shown in these bottom plots, the shape of the wave at some certain final time, and compare those results, and then eventually study the relativistic effects on absolute stimulated Raman scattering. But for now, that's all I have. So thank you if there's any questions.
Thanks so much, Jenny. So how do you hope to use this research in your sort of next steps, either in your continued studies or a potential career?
So most of my studies have actually been in relativistic stimulated Raman scattering. So I looked at something before called Landau damping and relativistic effects on that. And so this is just kind of a continuation of my research. And we hope to use this to look at more, right now these were very simple, basic simulations. We hope to look at more relative simulations with more realistic parameters in them and actually observe the effects of this scattering on more relative scales.
Got it. So what inspired you to go into this field of study?
I am a math student, and at first when I started this, I was just running simulations on something called the Vlasov-Poisson equations, which pretty much show the distribution of the particles within a plasma. And then kind of once I got into that, it was, well, relativity has an effect on it. Well, let's study relativity. And it just eventually ended up here.
That's amazing. Our board chair at the foundation was a math major, and she always loves to meet math folks and where that discipline can take you. So thank you so much today for joining us today, Jenny. Let's move on to Matthew Landon. He's with the Georgia Institute of Technology. Matthew, thanks for your flexibility. We'll have you jump in and then hopefully have Wei-Shan next.
So, hello, everyone. My name is Matthew. I am a PhD student at the Georgia Institute of Technology studying information security. And I have about 1 to 2 years left in my program. This summer, I worked on a project that was detecting targeted cyber attacks using reinforcement learning. There have been several cyber attacks on power grids, which could cause blackouts, endangering operators, and degrading national security. These attacks must be detected as soon as possible to minimize the attack damage. Traditionally, intrusion detection systems analyze the control network or readings from sensors in the grid. Unfortunately, motivated attackers have shown that they can bypass these systems and cause damage. In contrast, the project considered both the cyber and physical environment to detect attacks. To enable this analysis, I focused this summer on building a cyber physical simulation based on a real grid control network. Given a physical grid, there are several places that are controlled by the operator, including switches that disconnect lines and meters that measure the demand for power. For each, there's a network device in my simulation that it connects to. These devices are all connected to the switch. There is also a control center that has a workstation where operators monitor and control the grid. All the nodes are connected through a router. With the network set up, data flows between the control center and the grid controller. I built the simulation using the multi-lab co-simulation framework called Helix that allows multiple high-class simulators running at different time scales to operate with a unified progression of time. Now that we have the simulation, the question remains, how do we use the different types of data for attack detection? Is it impractical to use all data sources all the time? In the project, we use reinforcement learning to detect attacks. Given the co-simulation, our detector can either challenge a node to determine if it's operating correctly for a small negative reward, or declare that a node is under attack for a larger negative reward. The negative rewards train the agent to use a smaller number of actions to detect an attack, as each one requires time and personnel to carry out. Attack detection alerts that our system generates can signal grid operators to respond to attack as soon as possible, minimize the damage the attack can cause, and protect the security and safety of the nation. Thank you for my time. I can answer any questions. Yeah.
Thank you very much, Matthew. Really relevant research, especially to Livermore's expertise. So I'm sure it was an interesting summer. What is next for you?
So I have about a week and a half left in my internship. And with that, I plan to create more sophisticated cyber attacks within our simulation to see how well our attack detection mechanism can detect the more sophisticated attacks.
Fantastic. Well, thank you so much for sharing your talk today. Again, as I said, right in Livermore's wheelhouse. So good luck with the remainder of your internship.
Thank you.
Thank you. I'm going to move us on to our next speaker, who is Wei Shan. He's from UC Berkeley. Wei Shan, you're up next.
So hi, everyone. I'm Wei Shan Quinn, and currently I'm a third-year chemistry student at UC Berkeley. And this summer, I've been kind of just working with polymer research. And what's been really interesting to me is I've actually found that we can recycle these polymers and use them in a variety of ways for 3D printing. So we can actually create a really great upcycling of our products. So that would be kind of what my project is on, that I'll be talking about today. So just to recap, I'm Wei Shan Quinn. I'm a third-year chemistry major at UC Berkeley. And my project this summer was on recycling polyurethanes into 3D printable photopolymers. Okay, so on a global scale, sorry. So on a global scale, we produce 24.7 million tons of polyurethane plastics, which are used in everyday consumer items. Unfortunately, only 5% of these plastics can actually be recycled and thus heavily contribute to our global pollution endemic. Current methods to break down these polyurethanes, for example, a couch, require a lot of heat and energy and ultimately lead to low-value materials that degrade over time. So in my research this summer, I found a simple and elegant solution to this problem. I've shown that you can break down a rigid subset of polyurethanes called thermosets by simply adding together the polyurethane film and allyl alcohol in a bottle under room temperature to yield high-value urethane resins without expending any energy. And after this, we can take the depolymerized urethane resin and 3D print it with light into a variety of upcycled products. And since the 3D prints themselves can actually be depolymerized in bulk, not only is this process scalable, but ultimately we can form a self-sustained and green loop of recycling plastics, only using allyl alcohol and light. So as a demonstration, I created a polyurethane thermoset film and depolymerized it into a liquid with allyl alcohol, base, and THF solvent, simply under room temperature. And as you can see on the right, we actually see that it breaks down in the bottle. And so looking more into the chemistry of this, when these thermoset films form, their cross-link network gives them a large amount of strength. And what's rather remarkable is that this network is easily broken down by a simple substitution reaction with allyl alcohol and yield our high-value products for 3D printing. And next, we take this depolymerized mix and we can photocure it into a film. And once again, we can go back with allyl alcohol and depolymerize that again. So you see we form this recycling loop. And so even though this rectangular photocure may seem unassuming, it serves as a proof that our depolymerized mixture can be shaped and functionalized into an endless variety of products with 3D printing. And this step will be carried out in the coming weeks. Currently, though, I've been running a number of experiments to tune the purity of our samples, as well as understand how the substitution reaction works at a molecular scale to provide even greener options for depolymerization. Ultimately, I hope that by optimizing the depolymerization process to yield higher purity urethane resins, we can accelerate our idea from a scientific concept to a tangible industrial reality, bringing us closer to solving the global issue of plastic pollution, only using some light and alcohol. Thank you so much for all of your time, and I'd love to answer any questions.
Thanks very much, Wei Shan. I'm glad we got our slides underway. So where do you see 3D printing maybe going from here? The growth in the technology has been amazing.
Yeah, I mean, the technology we have at AML, or the Additive Manufacturing Lab, is just fantastic. We have volumetric additive manufacturing where you actually print as it's going around in a circle and you can print it all at once. And, you know, there's just a bunch of techniques. So I think this is really great that we can actually take our waste plastics and convert them into meaningful products with printing. So I think there's a lot of new work to be done in this area. And so I'm really excited about it.
Did you and your team talk about how this might scale to the, the volume of the problem it's trying to address?
Yeah, so what's fantastic about this is that as you all saw, we can actually take like a bulk film and depolymerize it. Definitely one of the things that we want to experiment with is the purity that we can get out. So we make sure that the quality of our products are really great. And actually with one of our formulations, we found this like really fantastic purity in it. And that's kind of an entirely new project. So I'm really excited to see where that goes. But yeah, that's kind of where we're projecting where this goes. I mean, it's definitely applicable, but it will take time and resources and effort to put in.
Very cool. And how are you hoping to use research like this into your next steps, either educationally or career-wise?
So I'm hoping to go into grad school after I finish up my undergraduate degree. And I've really enjoyed the work with polymer science. So it's definitely an option for me in grad school. But I'll be continuing to explore research areas and kind of see what best fits me. But it's been a fantastic internship this summer.
That's great to hear. Well, thank you so much for your talk today. Great job.
Great.
I'm going to move us along to our next speaker. We have Shikun Liu from UC Santa Barbara. Shikun, thanks for being here.
Thank you. Thank you so much for the introduction. It's my pleasure today to share my summer work about ALS-related protein TD43 aggregation versus assembly. ALS is a neurodegenerative disease that kills motor neurons, causing muscles to weaken and eventually paralyze, like Professor Stephen Hawking. The cause of ALS is not known, but in 95% of ALS patients, a protein called TP43 mislocate from the nucleus into cytoplasm and form abnormal aggregates that eventually leads to cell death. This makes TP43 aggregation a hallmark of ALS. For healthy neurons, TP43 also form assemblies and undergo liquid-liquid phase separation under stress. But once the cellular stress is removed, these assemblies dissociate. It's widely believed that the physiological assemblies are related to the pathological aggregates, but we don't know what causes the transition from the reversible assemblies into irreversible aggregates. To answer this question, I run molecular dynamics simulations. First, I need a full-length model of TP43, but a full-length structure of TP43 is not experimentally resolved. What we have is the structure of N-terminal domain, two RNA recognition motifs, REM1 and REM2, and an alpha helix fragment in the C-terminal domain. By connecting these four fragments using disordered loops, I obtain a model of the full-length TP43. However, TP43 proteins form dimer under physiological conditions, so I need to build a dimer model. To build a full-length dimer model, I extended the non-N-terminal dimer with the full-length TP43 model to build a full-length dimer model. There is also research showing that the size of the alpha helix affect the aggregation, but it's not clear whether it promotes or prevents the aggregation. To answer this question, I run molecular dynamics simulations on the full-length dimer model with different sizes of alpha helix, that is full helix, half helix, and no helix, and calculate the interprotein context between different regions. As we can see, the N-terminal domain has strong context because the dimer is bounded by the N-terminal domain, but on average, the C-terminal domain has the most context, which indicates the C-terminal domain plays an important role in the aggregation. As the helix size decreases from full helix, half helix to no helix, the number of contacts actually increases for REM2, CTD, and helix domain. No helix model has significantly higher contacts in the C-terminal domain compared to the full helix model. This indicates that a decrease in the helix length will overstabilize the dimer, which eventually leads to the formation of the pathological aggregates. These results also enable us to predict ALS-related mutants. If a mutant decreases the size of helix, this mutant is more likely to cause ALS. And thank you for listening.
Thank you very much. This is a topic that's very near and dear to our hearts at the Livermore Lab Foundation. What led you to focus on this topic? And what are you thinking about next?
Yeah, actually, back in grad school, I studied Alzheimer's. It's also a neurodegenerative disease. But for that disease, it's a protein called amyloid beta. And we also found that people who have Alzheimer's has a higher chance to have ALS, and people who have ALS also have some similar symptoms to Alzheimer's. And that makes me interested in the ALS. And for ALS, it's the protein called TP43 that caused the problem. And that's how I transitioned from Alzheimer's to ALS.
Very interesting. Yes, some of our early stage projects were focused on ALS, and we quickly learned that there were broad applications for the, across the range of brain disorders and disease. So did you come across any research in terms of how it affects the veteran population? I'm just curious.
Yeah, because for those veteran population that actually have a higher risk to get ALS, we haven't figured out why, but I think it's related to some brain damage. But my research mainly focused on the protein, so we haven't reached that step yet.
Got it. Do you hope to continue this kind of research in your next steps, either career-wise or at school?
Yeah, definitely. We are actually designing some small molecules that can target the TP43, and they are probably like potential drug candidates. So I'm very excited for that project.
Really important work. Thank you, Zikun, so much.
Thank you.
I'm going to move us to our next presenters. This is our tag team of 2 students that work together, Urwa and Kaylee. You'll be next. I'll let you introduce yourselves because I wasn't sure who was going to go first, but you guys are next.
So hi, my name is Kaylee Wong, and I'm a second year at UC San Diego studying mathematics and computer science.
And my name is Urwa Mir. I am a third year going into UC Davis studying computer science. Today, Kaylee and I are going to be talking about Launchit and the development and integrations that we added to Launchit under the DevOps internship team. So Launchit began as an internship project for the 2021 Do It team and was continued by the WEG team. It's a user-facing web application that allows users to deploy and manage persistent data services. So persistent data services include databases, message, broker, and queuing systems, as well as object storage. So prior to the creation of Launchit, in order to allocate PDS instances for themselves, users had to create a ticket and email back and forth with our admin team in order to allocate it. But now with Launchit, they can instantaneously create PDS instances for themselves.
Yeah, so the first project I worked on for my internship was a user interface design improvements for Launchit. My goal for this redesign was to take the pre-existing outline of the application and update it to be more visually appealing and intuitive for users. Throughout the entire redesign process, I had a few design goals and principles I wanted to keep in mind. The first was consistency in the typography, graphics, shapes, and color scheme. The second was visual clarity by creating a visual hierarchy and keeping simplicity and white space in mind. And the third was improving usability of the application by incorporating visual association, descriptors, animation, and responsiveness. I'll point out some of these ideas in my design choices on the next slide. And for the redesign process, I began with wireframing, which is a process designers use to create outlines of their products and establish the structure and the flow. And I used the design software Figma to do this. And to implement these redesign changes on the front end, I used HTML5, CSS3, and the Bootstrap 5 CSS framework. So here I've included images of the Launchit application interfaces before and after my redesign. In regard to the design goals and principles I mentioned earlier, for consistency, I wanted to create a brand for Launchit with consistent font styles, graphic styles, rounded shapes, and a blue color scheme. For visual clarity, I used colors to emphasize different sections of the page and to create a visual hierarchy, and also made sure to keep the design balance with white space just to avoid overwhelming users. And finally, for improved usability, I incorporated more graphics to improve visual association with actions. And I also added descriptors such as to the catalog and dashboard buttons on the landing page to make actions clearer for users.
So the first project I worked on with Launchit was integrating Mattermost. So what we did was create a notification system that would help our admin team keep track of the creation and deletion of PDS instances. So in order to do this, I created a logging function using the Mattermost webhook and generated comprehensive logging messages that would include information such as the user who created or deleted the instance, the namespace the instance was created or deleted in, and the resource name and type of the instance. So we can see at the bottom here, I have a couple of examples of what these logging messages would look like in Mattermost. So I integrated this new logging functionality into pre-existing logging classes. These logging classes would log PDS creation and deletion to Splunk and a MongoDB, and now Mattermost as well. So Kaylee and I then began to work on a group namespace functionality. So prior to us implementing this, there was no real way for users to collaborate and share project resources. So our goal was to implement a feature that would allow users to add other users as different roles onto various projects. We did this using the OpenShift API. So on the front end, we used HTML5, Jinja, CSS3, and Bootstrap 5. On the API layer, we used OpenShift, and on the back end, we used Flask and Python.
For the interface for this feature, we wanted to make it accessible from 2 locations. the dashboard with the complete list of projects a user has access to, and also within the dashboard for that specific project. In terms of the user design for this interface, we wanted to ensure it was as intuitive as possible for users. So we imitated the OpenShift interface, and this way users are already somewhat familiar with the new feature. And we also made sure to provide lots of user action feedback through displaying loading animations and success and error messages.
On the back end, we added in functions to add, delete, and get a comprehensive list of user roles. We did this using the OpenShift Wrapper API to create these requests.
To connect the front end and back end portions of this feature, we use Jinja dynamic HTML templates to display information according to the logged in user. And we also used the Flask web framework to collect and process a user's desired actions through forms on the front end. And this includes data such as the type of action a user is requesting, the project they're requesting it for, and also the user and role they're requesting it for. And using this information, we're able to request and receive information and actions from the backend functions to the OpenShift API.
So in addition to these functions, we also created a logging class that would help us keep track of the creation and deletion of different roles. So these logs are saved to Splunk as well as the Mongo database and also sent to Mattermost, which we talked about a little bit earlier. In addition to the logging, we also used PyTest to create comprehensive test cases to ensure adequate code coverage. So we would test both successful and failed runs of our functions. We would test with valid input to make sure that it succeeded with valid input, and invalid input to make sure that our functions would fail safely.
Yeah, so these are the developments and integrations we've implemented for Launchit so far. And we're currently working on more features and integrations, including allowing users to add and delete new projects, and also integration with StorageGRID object storage. Thank you.
Thank you both so much. Great presentation. One question is whether you guys plan to continue to collaborate together. I know you're at different campuses, or while you're right around the corner at Las Positas, which is exciting to see. Do you guys have any plans to continue working together or with the larger team?
Yeah, definitely. I had an amazing time working with Kaylee. She is great with the front end stuff, and I've learned so much from her. So I would absolutely love to continue working with her.
Fantastic. And have you shared any of this research with the Launchit company?
So Launchit is actually an in-house LC solution for the PDS allocation. So we are actually, this currently isn't in production quite yet, but our older version of Launchit is in production. So this will go into production pretty soon.
Super. And can you give, just for those of the viewers who maybe are less familiar with the origins behind the Do It project, I think you mentioned, can you give just a quick background on that?
Definitely. Kaylee, do you want to take this one or?
Yeah, sure. So the Do It program is basically the DevOps internship team. And it was a new internship program started by our mentor, Otto Venezuela, actually last year. And so Launchit was the project that the interns first worked on last year. And so it was continued by the web team. And now this year's Do It team is working on more features and integrations for the application.
Super. Thank you so much. I'm going to have to move us along, keeping an eye on the clock, but great to have you both today.
Thank you.
I'm pleased to introduce our next speaker is Marianne Mort. And Marianne, I think you said you've got your slides managed on your end, so I'll hand it over to you.
Hi, everyone. My name is Marianne, and I am a graduate student at UC Davis in electrical engineering. And today I'm going to talk to you about the multi-frame gated X-ray imager, which is a proposed target diagnostic to be used at NIF, the National Ignition Facility. Okay. Diagnostics are super important for us because they help us make improvements every step of the way so we can more efficiently reach ignition. And so we can get closer to a clean, renewable energy source. This is important for X-rays that come out of the imploding fuel capsule because it happens so fast, and these x-rays are such high energy that it can be hard to image them with decent enough temporal and spatial resolution. So the MGXI will take several frames of the imploding fuel capsule, basically making a movie of it. So the way that works is the x-rays will enter this vacuum window and go towards this microchannel plate. As you can see, there's a bunch of channels here, and as an electron enters one of the channels and hits the wall, a secondary electron is emitted, causing a cascade effect, giving us a signal gain. This is important because even if there's a single electron event, there's enough signal that an image can be captured. So once we have our signal gain from the MCP, it goes towards our HCMOS sensor, which captures several images that are a few nanoseconds wide, and that's what gives us our movie. So I've been taking a two-prong approach, working on two different things at two different labs simultaneously. First, at the Livermore lab, I've been using a class 1 laser to test this HCMOS sensor here at this setup. Eventually, I will be using this HCMOS sensor at my setup at UC Davis, where I've set up this vacuum system with fixtures that hold my MCP and an electron gun as my source. From my initial results of testing the HCMOS sensor, I've been doing two different modes of testing. These plots at the bottom here show the high-speed timing mode, and this 10-10 gate profile basically just means 10 nanoseconds of collecting data and then waiting 10 nanoseconds before the next frame is collected. These are basically our 4 frames of data that's collected, which gives us our movie. The other mode is this manual shutter mode, which basically just means long integration times. And this is the mode I plan on using at UC Davis. So there's a lot more for me to do, but so far we're looking good. Thank you.
Thanks very much, Marianne. What led you to get involved in this research area?
Yeah, so this is actually my dissertation project for my PhD. So I've been working on it for a couple years now. I basically got a call from my advisor saying, "Hey, do you want to work on this?" And I was like, "Yes, I really do."
Oh, that's terrific. I know Livermore and UC Davis have a long history of collaborating together. So it's great that you'll be taking this research back with you as you continue your PhD. One question from the audience: how do stray magnetic fields affect the detector performance?
Yeah, hold on. Let me go back to the first slide if I can. So we do have a solenoid that surrounds our detector here, basically confining our signal from so it spatially doesn't move too much, and then so that we can like capture our image. So also most of the detectors that we use have shielding around them. So I assume that would
help
protect from most of the stray magnetic fields.
Got it. We got another question from the audience. Does the number of frames affect the temporal resolution?
Yeah, so this image here actually is straight from the sensor. This little dot is our class 1 laser. The sensor actually has 2 hemispheres. So if we center the signal right at the center, we can collect 4 frames from the top side and then offset and then collect 4 more frames and then like intertwine our data and basically give us even better temporal resolution.
Great, thank you so much. I'm going to move us along because I'm looking at the clock. Thank you so much, Marianne.
Thank you.
Our next speaker is Jacob from University of Colorado at Boulder. Jacob, you're up next.
Hi, everyone. My name is Jacob. I'm a PhD student at CU Boulder in applied mathematics, and I've been working with Kenny Weiss on a problem involving using winding numbers to solve containment queries. So let's take a second to talk about containment. Are you all contained in the room that you're in right now? You'd be able to tell if you could stand up, look around in a circle, and if everything you see is a wall, then yeah, you're contained in the room that you're in. But what if there's an open door in that room? I mean, we all kind of understand that you're still contained in that room, but how big does that door have to be until that's no longer the case? Well, mathematicians have a name for this concept, and we call it the generalized winding number, which is basically a fraction that represents the amount of in a roomness that a point has with respect to the walls around it. We care about this value because it's really important in a lot of different physics applications, probably even yours, to know if a point is contained within some boundary. For example, if your domain has multiple materials in it, and you're given some random point, a quadrature node maybe, you need to know what material that point is in. So how are we going to solve this? Well, I'm working in a software package at the lab called Axum, which is all about performing these simple kinds of geometric operations really efficiently. But as of now, all these containment methods require you to linearize your high order curve, which, as you can imagine, is going to either hurt your accuracy or your runtime. What's more is that these implementations perform, to put it lightly, catastrophically on meshes that are not perfectly designed. And it isn't always obvious when that's going to be the case. Take, for example, this car here. Look closely and you can see that the front wheel is completely embedded within the rest of the car. That's not good for our methods. Gaps are even worse. If your mesh isn't totally watertight at every single one of its vertices, the current methods will just zoom in and refine on those areas.
Jacob, I'm sorry to interrupt you.
Run out of RAM.
Jacob, I'm so sorry to interrupt you. The slides aren't advancing, so I don't know if it's on actual slideshow. We're just still seeing the first page.
Here. Okay, well, can you see this?
Yeah. Okay. Yes.
Go with this then.
A little bigger. Thank you. Sorry.
Well, this was the picture for if you're contained in a room right now. The problem being that the current methods we have in Axum have these limitations, namely that you need to linearize your curve, you need self-intersections, and you need your bounds to be watertight. So what we're going to do about this is we've used an algorithm with the generalized winding number, which basically is an integral. If you're a mathematician, you may recognize it as the Cauchy integral formula that gives us exactly what our winding number is in 2 dimensions. So if you, so what we've done at the lab here is develop an algorithm that can efficiently and consistently evaluate this integral for any curve that you give us. Take, for example, this one on the left here. If you look at it on the top, we have a gap. And if you look at it on the bottom, we have an overlap. And these are the things that the current methods have a lot of difficulty with. But with this current method, we just solve this integral for each individual curve in that shape, and we just add up the numbers when we're done. We get this area at the top where if you look at it, the gap is kind of just this small area where the area inside spills out. And that's where we get our idea of robustness. The places that we expect to be mostly inside are still mostly inside. And the same is true for the areas on the bottom. They're still mostly outside. It doesn't fix the problems in the mesh, but it at least keeps them local to where they were originally. So if this sounds like it's of any interest to you and could be of use in your project, please come check us out at our GitHub link. Thank you very much.
Thanks so much, Jacob. I apologize for interrupting.
Oh, no worries. Thank you for interrupting. Actually,
really nice presentation. Can you comment on what led you to this field of study and how you got into this?
So my background is in both mathematics and computer science. And so I originally did a project in a tangential field related to these volume fraction initializations in undergrad. And that just happened to find its way to my mentor here, who reached out and asked if I'd be interested in working on this project, which I absolutely was.
And was this your first time working with Livermore Lab, your first internship?
Correct. I've had a great time.
Good to know. Well, thank you so much, Jacob. Really great talk. I'm going to move us along. If you can stop sharing, great. So we've got our last 2 speakers. I think we're going to make it in time. I'd like to introduce Emma. She's our next student. Emma, you're on.
Hello, everyone. My name is Emma Van Hoekmode, and my mentor is Ryan Mohan. And today I'm going to illustrate how ByGANs can aid in the analysis of network traffic. So as scientists, we know the value of data, and more importantly, the danger if that data were to fall into the wrong hands. Sensitive data such as social security numbers and other identifying information could be stolen and used in malicious ways. Additionally, data can be held ransom. A huge component of mitigating the effects of a cyber attack is to be able to identify when one is happening as quickly as possible. One way of doing this is by examining network traffic data. But how can we identify a discrepancy quickly, efficiently, and accurately? This is where BIGANs come in. A BIGAN is a bidirectional generative adversarial network. BIGANs allow us to not only identify when there is an anomaly, but shows us exactly where the anomaly occurred. BIGANs build off traditional generative adversarial networks, or GANs for short. A traditional GAN utilizes a generator and a discriminator. The goal is to train the generator to create fake data that will deceive the discriminator, and to train the discriminator to distinguish between real data and fake data provided as input. So the model is essentially playing a game against itself, where one component is trying to trick the other. BIGANs build off traditional GANs by adding an encoder to the mix. This diagram shows a high-level overview of the BIGAN architecture. The encoder maps the data to a latent representation, while the generator maps a latent representation to data. Hence, it is bidirectional. Both the generator and the encoder provide input to the discriminator. So now the discriminator is trying to determine whether it was given real data and a fake representation, or fake data and a real representation. During training, the encoder is mastering how to map the original data to its latent representation. If the data has an anomaly in it, the encoder will try to compensate when creating the latent representation, causing a discrepancy and highlighting the anomalous data. So the central focus of my summer project was to test if BIGANs could be used to detect anomalies in network traffic. The paper-efficient GAN-based anomaly detection claimed to have highly accurate results when running a BIGAN on the KDD-CUP dataset. The KDD-CUP dataset is an immensely popular network traffic dataset, but it is highly skewed and contains many redundancies. So my mentor, Ryan, created a model following the scientist's implementation, but was unable to replicate their results. I conducted research to find alternative datasets to KDD-CUP that fixed its faults. I discovered NSL-KDD, which was a derivative of KDD-CUP. This dataset was less skewed than the former due to the absence of redundancies. We also looked at the code the scientists provided in the GitHub closer and discovered that the data was not being pre-processed correctly. I then pre-processed the NSL-KDD dataset the correct way and ran the model. The results were promising. Here is a graphical representation of the loss functions, which shows that the model is learning as expected. The overall accuracy of distinguishing between anomalous and non-anomalous traffic came to be 93% for my initial tests. Having a model such as this can identify attacks quickly, efficiently, and accurately, so you and your data are better protected in this virtual age. Thank you for your time. I'll be happy to answer any questions you may have.
Another really timely subject from today's talk, so thank you so much. How do you plan to continue your research in this area, either in school or beyond?
Well, thankfully, I still have quite a bit of time on my internship, so I'm still working with Ryan on running this on new data sets and figuring out ways of making it even more applicable to wider applications, I suppose.
Yeah, and Emma, can you comment on what led you to pursue this field of study?
Yeah, so I always just thought it was important to protect those that may not be able to protect themselves. And I feel like computer science especially has a lot of applications in that area. And with like virtual attacks just getting worse and worse, it's more important now than ever for us as computer scientists to step up and do what we can to help those.
Thank you. It's a really powerful illustration of leveraging the lab's expertise for the greater good. So thank you very much for joining us today.
Yeah, thank you.
Okay, that brings us to our very patient final speaker, Colt Whitley. And we're going to hand it over to you, Colt.
Hi, everyone. My name is Colt Whitley. I'm an undergraduate from Cal Poly. And this summer at the lab, I've been working on a precision thermal control system for spacecraft. I did this work under my mentor, Jordan Carburn, as part of the Space Science and Security Program. So emission spectroscopy and transit emission spectroscopy are some of the strongest tools astrophysicists have for determining the atmospheric composition of stellar bodies. But to be confident in their results, they need to know that changes in the data they're being given is from physical phenomena and not from noise in their system. The work I've done this summer has been to create a closed loop electrical control system capable of keeping these detectors within 10 millikelvin of their set point, because thermal variation leads to high noise in these detectors. My work has had two main parts: developing a temperature sensor, which can precisely measure small changes in temperature and convert that into a filtered discrete digital signal, and implementing a digital PID controller on a microcontroller to regulate these sensors. So like I said, I've spent a lot of time focusing on developing a temperature sensor circuit. The circuit diagram we can see is right here on the right, and it's something called an Anderson constant current loop. This design and topology was chosen because it has many advantageous electrical characteristics for higher noise immunity. But even with that, when I simulated my model, the resistor thermal noise, BJT shot noise, and MOSFET flicker noise were so prevalent that we got the result you see in the bottom left. This becomes a big issue because this is the scale I want to be able to discern signals on, and it's far too noisy. As such, time was spent implementing passive filters and discrete filters. And the result of this filtration is that we were able to get this signal out from the same data. Using SPICE and Simulink, I simulated this circuit 200 times with random noise to create an ensemble. By taking a slice of this ensemble, I was able to get a distribution of the signals. The key takeaway here is that the filtration reduced the standard deviation from 33 millikelvin to 10 microkelvin, well within the acceptable range. The second half of my work has focused on the development of the control loop. The theory of operation for this is that we're going to cold bias these to optical sensors, and then we're going to use the control loop through trim heaters to regulate the temperature. The control law was developed on a simplified linear plant model of a lumped thermal circuit, and then it was applied to a nonlinear Simulink model, which we can see in the bottom left. After tuning this model on after tuning this control law, I was able to arrive at a solution that had less than 5 millikelvin of overshoot and a 30-second settling time, and more importantly, very high phase and gain margins, because this controller was tuned for robustness rather than optimal response. All of this could run on a slow 10 Hertz sampling rate controller. Going forwards, I plan on testing the hardware on a breadboard and coding and tuning the PID controller. Thank you for your time. I'd love to answer some questions.
Thanks very much, Colt. So you mentioned you're an undergrad at Cal Poly. What led you to this field of study, and how do you maybe hope to continue working on that as you return to campus?
Yeah, so I'm an undergrad, but my dad's a physics and astronomy teacher in high school. And so I've always loved space. And so any opportunity I got to work on something in space is super exciting. And my mentor did a talk at Cal Poly, and we hit it off, and it's just been an incredible opportunity.
Oh, that's fantastic. Yeah, sounds like you've really taken advantage of those opportunities. What would be sort of your ideal career, goal in this field?
I'm kind of young, and so like there's so many amazing branches you can go into. I think really just anything getting to contribute to working hands-on with satellites and space hardware that contributes to science, exactly like this mission is. So, yeah.
Terrific. Well, thank you so much, Colt. Great presentation. And I guess that brings us, we're almost at 1 o'clock here. So I want to thank everybody who joined us today for the program. This was a really exceptional group of young people who were working at Livermore Lab this summer, and we feel really fortunate to have had a chance to sort of peek into the research that you've all been doing. It's really, really impressive and gives us a lot of hope for the next generation of scientists and engineers that are moving into the field. I want to take just a quick minute. I believe we have Caitlin Keeshan from Assemblymember Rebecca Bauer-Cahan's office, who wanted to just say a couple of quick words in recognition of your great work this summer and in the SLAM. Caitlin, can you hear us? Are you able to hop on really quick?
Can you hear me?
Yes.
All right. It doesn't give me the option to go on video, but I'm here on audio.
Okay.
I just wanted, I'm Caitlin. I work for Assemblymember Rebecca Bauer-Cahan, who is the Assemblymember who covers the Livermore Lab. And it was such a pleasure to be here with you all this morning and early afternoon and hear about all your incredible work. we feel really lucky. Assembly feels really lucky to have such a powerhouse of science and technology right here in our backyards. And it's incredible to see a new, generation of scientists going out there and exploring all sorts of fascinating topics. So thank you so much for sharing. It was very, very enjoyable to be here with you today.
Thank you, Caitlin. So that concludes our formal program. I'd like to ask if our students can stay on for a quick minute. We'll try to take a screenshot for posterity. And for everyone else who attended today, thank you so much for supporting the Livermore Lab Foundation and this next generation of STEM leaders. Hope you have a wonderful day.